Hello, it's Ollie Epsom again, and I'm delighted to announce that after what seems like forever, but is in reality probably about 4 months of work, off and on at weekends, evenings and so forth, I've finally got my computer-controlled direct solar water heating system working. Let's take a look at it.
In this graphic we can see a schematic layout of the system. As you can see, it's effectively an open loop system which sucks water out of the bottom of the hot water tank, pumps it through the solar panels on the roof, and then drops it back into the tank again. Okay, so the system is controlled by a Raspberry Pi computer and a bespoke control box that I built myself. I put a lot of trouble into designing the system in the beginning to make sure that it would behave in a way that I understood. In order to achieve this, I had to use a lot of spreadsheets and draw a lot of graphs. I also completely modelled the entire assembly in SolidWorks, including my house, as we can see here, and in order to make sure that everything fit. I'll then use this information to create a full set of drawings, which I've got available should anybody else want them. One of the things that I think my solar hot water unit has that a lot of commercial units don't have, aside of course from being built by me and being cheap, is that it seems to have quite a sophisticated control system, which allows a variable pump speed to be used, which effectively means I can extract very high temperatures from the panel by reducing the flow rate under computer control. And this is something that I haven't seen in any commercial products. Building the hardware and the externally mounted equipment, such as the panels and plumbing them in, was, if anything, probably easier than building the control unit and software, at least for me. I started off, as I said, by modelling it in CAD, and because I had all the drawings out in front of me when I was building it, actually the build itself went pretty straightforwardly. Difficulty was getting it up onto the flat roof, since each panel probably weighs around 60 kilos, but I luckily had some friends round to help me with that, and once installed on its frame, the whole two-panel system is extremely sturdy and doesn't seem to shift around a lot in the wind. So far it's all looking pretty good.
Here we have, albeit in bits at the moment, ticking away the control unit and the Raspberry Pi computer. Here we can see what it's doing. It's a bit crude at the moment. This system controls via this umbilical cord in the airing cupboard a pump, which is here, a flow meter, obviously that's just for our benefit, and you can see it's currently spinning round, and we also have two motorised valves in there as well. The heat for this system comes from the two very large solar panels which I've built on a flat roof out there. You can just about see one of them in the corner. Okay, it's worth taking a look at how the system works, because it is quite complicated and there's a lot of nuances to it. The software I'm still tweaking to get the algorithms right. I've literally just got it working about an hour ago. Heated up quite a lot of water since then, and just for the benefit of users, it's the 5th of October 2013 in Derby in the UK, so if you're getting any heat in those conditions, it's reasonably impressive. At the base of the system we have effectively the hot water tank here, which I've heavily re-insulated. Now, it was the tank that originally came with this very old house, so it's not been specially insulated like a modern tank. However, I'm losing about 36 watts of it. I've got two LM32DT calibrated sensors, one at the bottom of the tank and one at the top, and then out on the panels themselves, out the back there, I've got a total of 4 sensors. The same type. I only need one, however I've got 4 in case they fail, 2 per panel, and I can select them with this switch here. That's just one, we don't want to start going into panels without needing to, so if a sensor fails we just swap over, and 2, out of curiosity really, to see how the system works. The control input to the system is merely in the form of pulse width modulating the pump motor. We do have 3 other possible outputs, which are the 3 motorised valves. Now, I've described 2 motorised valves under here, the airing cupboard on the suction and discharge sides. There's also a third outside on the panels, And that third motorised valve is used to drain the system if it looks like it's going to get cold. Effectively, unlike a lot of more sort of commercial systems which use a separate loop inside the hot water cylinder and circulate glycol through the panels, I've used effectively an open loop system, so I circulate normal water through the panels, which does put it to the risk of freezing in the winter months. However, it was a lot cheaper to do it like that, so if it does freeze, the computer will simply isolate the suction and discharge valves, open the drain valves, and put the system to bed that way. On the computer screen, it's a bit crude at the moment, but effectively what it's telling me is the sensor readings. The figure on the left is for the photovoltaic cells I've got on the top, because this system also provides hot water by modulating the immersion heater to regulate it by way of the power coming in from the PV cells, as described in one of my previous videos. So these two systems work together. Now, usually once a system is up and running, the temperature differential that it uses to calculate the pump speed is based on the difference between the top or delivery side of the tank and the bottom or suction side of the tank. Effectively it sucks water out of the bottom of the tank, pumps it through the panels and dumps it in the top. The location of the sensor on the top of the tank is on that discharge side. Therefore, once the system is operational, the temperature that you are interested in as a user is the delivery temperature to the tank. However, to get the system going, it uses the panel temperature. In a perfect world, the panel temperature and the delivery temperature would be exactly the same. However, you do lose heat between the two, which is the first thing. And the second thing is the panel sensors are on the aluminium heat recovery plate, not in the actual water on the panel. So there can actually be a significant, and I'm talking maybe 20, 30 or even 40 degree differential between the two because of the heat transfer characteristics of the panels. That, to be honest, is a figure that would be improved if you bought commercial panels or you were a better builder than I. So it starts off by using the differential temperature measured from the panel, pumps through about 3 litres of fluid, which it knows because I've calibrated the pump, and that's enough to warm the pipes up, after which it then reduces power as appropriate depending on the temperature differential. You then simply leave it to do its thing. I'll give you further news on this system as time goes on. Thank you very much.